Hello everybody, this is Homer White, back again with the fourth part of the 10th chapter of our book. We're working on tests of significance. In this part, we'll look at a couple of tests for one population proportion p. The first one will be based on the normal approximation to find p-values, and the second will be an exact test that's based on the binomial distribution. We'll also look at a test for the difference of two population proportions, p1 minus p2. Always remember to make sure that the necessary packages are loaded. First, let's talk about the test for one proportion that's going to be based on the normal curve approximation. Say we have this research question: are a majority of Georgetown College students female? We'll investigate this question inferentially with the Math 111 survey data. The first step in a test of significance is always to define a parameter and to state the hypotheses. This time, let's let P be the proportion of all Georgetown College students who are female. As for our hypotheses, we're wondering whether or not females are in the majority or not, and 50% is the borderline between majority and minority. So it makes sense to let the null hypothesis claim that P is 0.50. The alternative, which claims that the females are in the majority, is that P is bigger than 0.50. Notice this is a one-sided test. Partly we're doing this just for variety, but also data in past years has shown that Georgetown College has had a majority of female students. So in order to incorporate this data-driven knowledge, we can use a one-sided test for the current year's data. Note also the notation P0 will be the null's belief about the value of P. So in this test, P0 has the value 0.50. We use the same function as we use to construct confidence intervals for one proportion based on the normal approximation. That's prop test GC. The formula data input is the same as it was for confidence intervals. We also need to specify what the successes are that we're counting up females. But if we want to test in addition, then we need to set the P argument to 0.50, the null's belief about P. And we also need to specify the side if we're not doing a two-sided test, so we say that alternative is greater. If you'd like a graph of the p-value using a normal curve, then say graph is true. Let's take a tour of the results. If you were to run this code, you would first see some output to the console that gives you descriptive results. In the 71 students sampled, 40 of them were female. The sample proportion is 56.34%, the 0.5634 that you see here. We're counting up females. Those are the successes. Thus, we have 40 successes and 31 failures. We have more than 10 successes and failures, and so we've met the cutoff for the safety check in prop test. The safety check for a test of significance is always the same as the safety test for confidence interval to be reliable. The other part of the safety check is, was your sample like a simple random sample from the population of interest? We're supposing that's the case for the Math 111 survey data, so it looks like we're safe to proceed. Moving on to the inferential results in the output. P hat is our estimator for the population parameter P, so that's 0.5634. The standard error for P hat is computed as 0.05886. That's about 5.88%. Let's think about what this all means. The null hypothesis expects P hat to be around its P0 value of 0.50, give or take some for chance error. We actually got P hat was 56% instead of the expected 50%. This is 0.0634, 6% more than what the null expected. But if you think of this in terms of standard errors, you see that 6% is really not much more than one standard error above what the null expected. So our results don't seem so surprising if the null hypothesis is correct. Already, long before we get to the end of the test, we can see that we're probably not going to be rejecting the null hypothesis this time. Moving on to the test statistic, which is called Z in this type of test. The test statistic is approximately given by the following formula. Sample proportion p hat minus the null's expected value for this sample proportion, p naught, divided by the standard error for p hat. So again, what you see in the numerator is the observed difference between the results that you got and the results the null was expecting. And this observed difference is being compared to a standard error for the estimator. So we've got z-score style, yet again, for our test statistic. This test statistic is telling you how many standard errors the p hat is above or below what the null hypothesis expected it to be. Well, actually, to be perfectly honest, it's telling you about how many standard errors above or below. The reason is that it's only approximately given by the formula that we show here. What actually is going on is something called a continuity correction, and we're going to explain that very soon. Let's move on now to the p-value. The p-value is given as 0.1692. Let's think about what it all means. Remember that z depends on p hat. That was in its formula. P hat is a sample proportion. It also depends on the standard error for p hat, which has a p hat in its formula anyway. So in a couple of different ways, z depends on numbers that depend on the sample, and the sample depends on chance. So z is a number that depends on chance. Therefore, it's a random variable. As a random variable, it's got some kind of probability distribution. And the fact is, it has a distribution that's approximately normal with mean 0 and standard deviation 1. We'll go over again why that is so in just a little bit. Now the p-value is the probability that z is at least as big as the value that we actually got in the study, given that the null hypothesis is true. That's given symbolically down here. Because z has approximately a standard normal distribution, mean 0 and standard deviation 1, we can find that p-value approximately by looking under the density curve for a standard normal past the test statistic that is given. This shaded area approximates the p-value, and that shaded area comes out to 0.1692. Let's interpret this p-value for ourselves. If 50% of all Georgetown College students are female, then there's about a 16.92% chance of getting a test statistic that's at least as far from 0 as the one we actually got. Again, thinking this over, we see that the results of this study are not so terribly unlikely to occur if the null is correct. So when it comes time to make the decision, we note that the p-value is bigger than our usual cutoff of 0.05, so we're not going to be rejecting H0. And as for our conclusion, we can just say that the data did not provide strong evidence that a majority of Georgetown College students are female. Let's go back in and think about a couple of things in a little bit more detail. First of all, that normal approximation that was being used. Where did it come from? Well, let's let capital X stand for the count of successes in our sample. The variable sex has two values, female and male. That's like two outcomes in a binomial random variable. And we're counting up females, so females are like success. The 71 students in the sample are like 71 trials. Each one can come out male or female. Now, if the null hypothesis is true, then the chance of success on each trial is the 0.50 value, the p naught, the null's belief about p. So if the null hypothesis is true, then that count of successes has the distribution that's binomial with n equals 71 trials and chance of success equal to p naught, 0.5. Now we know some things about binomial random variables from previous chapters. We know that when the number of trials is big enough, the probability distribution for a binomial random variable looks a lot like a bell-shaped normal curve. Now let's think about p hat, which is the sample proportion. It's the count of successes divided by a constant number, the sample size, 71. When you divide x by 71, you're going to change the possible values. They're all going to be 71 times smaller than they were before. But you're not going to change the fundamental shape of the probability distribution. It's still going to look just as much like a bell-shaped curve as it did before you divided by 71. Therefore, p hat is also approximately normal as a random variable. Now let's think about that formula that gives approximately our test statistic z. It's this approximately normal random variable, p hat, minus what the null hypothesis expects it to be, the expected value, divided by its standard error. Now, the standard error for p hat is an attempt to approximate the standard deviation for p hat. And so this formula looks like random variable minus its expected value divided by its standard deviation, or at least it's close to that. Now, if you take a normal random variable and subtract away its expected value and divide by its standard deviation, then it becomes a standard normal random variable with mean 0 and standard deviation 1. Therefore, the test statistic z is approximately a standard normal random variable. All of this is assuming, of course, that the null hypothesis is true, that its expected value really is the p0 that the null believes in. We're going to get our p-value from this normal approximation. But now let's talk about the continuity correction. This is something that helps us to get the best p-value that we possibly can from the normal approximation. Think about what we really want. We'd really like to know, what's the chances of getting 40 or more successes in our 71 trials, like we actually got? Well, that would be represented by the shaded areas that you see in the graph before you. The graph before you is part of the probability distribution for a binomial random variable with 71 trials and chance of success 0.5 in each trial. And the shaded rectangles start at 40. Remember, each rectangle gives the probability that the binomial random variable will be exactly the value that it's centered over. So this leftmost shaded rectangle is the probability that the count of successes would be exactly 40. The next rectangle over is the probability that the count of successes would be exactly 41. And so on, all the way up to 71, but we really don't have room to show past more than x is 47. But that total shaded area from 40 all the way out to 71 is the probability that the count of successes would be at least as big as the count we actually saw in the study. That's the probability we would really like to have. We're planning to approximate that probability by the area under a normal curve. The graph that you see at the top, the curvy graph, is part of the graph of a normal curve that has the same mean and the same standard deviation as the binomial random variable under study here. As you can see, it approximates the binomial distribution pretty well, runs through the tops of the rectangles pretty well. Now sometimes it's above a rectangle and sometimes it's below, but you notice the times that it's above seem to cancel out somewhat times it's below for just about each one of these rectangles. So the approximation is going to be mighty good, I think. However, we do need to be careful. If we want the area under the curve to come as close as possible to the actual area of the rectangles, then we need to start the area under the curve at the left-hand endpoint of the rectangle centered over 40. That's so we can capture all of that rectangle. We don't want to start at 40 because then we'll miss the left-hand side of the rectangle over 40. So we're going to start the left-hand endpoint, and since each of these rectangles is centered over whole numbers that are 1 unit apart, each rectangle is 1 unit wide. The left-hand endpoint of the 40 rectangle actually is at 39.5. So we should try to get the area under the normal curve from 39.5 onward. That's a continuity correction. So how do we incorporate this in the computation of the test statistic? Well, p hat, officially, is the number of successes divided by 71, 40 over 71. But we're going to just say that there were 39.5 successes when we compute p hat. So 39.5 over 71 is going to be the value that we put in for p hat in that formula for the test statistic. That's how prop test GC works it when it's asked to do a continuity correction. Think about it. Without that continuity correction, the test statistic would be exactly the p hat minus the p naught over the standard error. So it would be 40 over 71 minus the p naught of 0.5 over the standard error, and it would turn out to be a little bit more than 1, about 1.07. The area under a standard normal curve past 1.07 can be found, and it turns out to be about 14%. But with the continuity correction, and this is the way that prop test GC actually operates by default, we're calling p hat 39.5 divided by 71. Take away the p naught, divide by the standard error, and you get a somewhat smaller number this time, the 0.9571 that's actually reported as the test statistic. And the area under the standard normal curve past 0.9571 we've already seen to be about 0.1692. So there's a difference here. Without the correction, the p-value would have been reported as about 14%. And with the correction, the p-value would have been reported as 16.92%, which is about 17%. 14%, 17%. The difference is nearly 3%. That's a fairly significant difference. So the continuity correction is fairly important to use at sample sizes that are not very, very large. For very large sample sizes, the continuity correction does not make too much difference. That's because for the binomial random variables in question, all of the rectangles are actually very skinny compared to the total distribution. And so missing half of a rectangle won't make that much difference. But also, the fact is, when R is dealing with binomial random variables at very large sample sizes, it actually computes probabilities concerning them using the normal approximation in the first place. But still, all this talk about exact binomial distributions gives us an idea about a possibly better test for one proportion. Let's think about this better idea. Again, let X be the count of successes. If the null hypothesis is true, we've seen that X has a binomial distribution with number of trials n equal to the sample size and chance of success equal to the null's belief p naught. And it has exactly this binomial distribution. So why not go ahead and base the p-value directly upon the binomial distribution instead of veering off into a normal curve approximation, which has to be corrected with continuity considerations? Let's try it for real with the same research question. Are a majority of Georgetown College students female? The statement of parameter and hypotheses is the same as it was before. The code's a bit different too. We learned how to make more exact confidence intervals using binom test GC when we were working with one population proportion. And we can use binom test GC to give us significance tests as well. We need to give it the same formula data input as we would with a confidence interval, and again we need to specify what our successes are. In order to get the test, though, we add the new argument p that gives the null's belief about what the population proportion is, and if our test is one-sided, then we need to specify the side. If you run this code and look at the output to the screen, you'll see that the sample proportion p hat is just the same as it was before, 0.5634. The standard error for p hat is computed just as the same as it was before, about 5.88%. Again, we've thought about it, and we know that if the null is correct, the number of successes x is a binomial random variable with 71 trials and chance of success 0.5. Now, no test statistic is actually given with this test of significance. If you look at the output, you'll see that. But if you like, you can think of those 40 successes as the test statistic. The particular value that x came out to be can serve as your test statistic in this case. The p-value is the probability that x, this count of successes, turns out to be at least 40, like it did in our study. The at least is because this is a one-side greater than test of significance. So if you were to ask for a graph of the p-value when you run binom test GC, you would actually get a graph of the distribution of the binomial random variable with 71 trials and chance of success 0.5. And the shaded area would be everything from the rectangle 40 onwards. That shaded area is our p-value, and it's approximately 0.1712. You know, when we did the normal approximation, we got 0.1692. So the difference is very small. The normal approximation was actually doing pretty well. But with no extra effort here, we've got a little bit more exact p-value. So binom test GC really is the recommended procedure for confidence intervals and for tests of significance, dealing with one population proportion. Quickly, the rest of the analysis. The p-value turned out to be 0.1712. How do we interpret that? Well, if only 50% of all Georgetown College students are female, then there's about a 17.12% chance of getting 40 or more females in a sample of 71, as we did in this study. So our results are not so unlikely if the null is true. The p-value is bigger than 0.05, so we're not going to reject the null. Again, the study did not provide strong evidence that a majority of Georgetown College students are female. Let's have a look at another example of a sort that often occurs when you're talking about one population proportion. A random sample of 2,500 registered voters shows that 1,325 of them favor the Affordable Care Act. Our research question is, do a majority of all registered voters in the U.S. favor the act? As for parameter and hypotheses, let's define P to be the proportion of all registered voters in the U.S. who favor the act. Again, because we're talking about majority versus minority, we set the null hypothesis right at the cutoff, 0.50. We don't have any prior data this time that guides us in one direction or another, so let's go for a two-sided test. The alternatives will simply be that P is not 0.5. Now the code. This time we have summary data. Just as with confidence intervals, binom test GC can handle summary data. You just set the argument x to the number of successes and the argument n to the sample size. And if you want to test, then you have to add the argument p, setting it to the null's belief of 0.50. This is a two-sided test, so we don't have to worry about the alternative argument. If you run that code and look at the results, you'll see that p hat is computed to be about 0.53, 53%. The standard error for p hat is computed to be about 1%. So p hat came out 53%, 3% higher than what the null was expecting. The standard error is 1%, so our results are about 3 standard errors above what the null hypothesis expects. That seems pretty surprising. In fact, the p-value is 0.0029. Since that's such a small chance, we're going to reject the null hypothesis. We've got strong evidence here that a majority of registered voters in the U.S. favor the act. Let's turn now to significance tests for the difference between two population proportions. First of all, let's look at the data frame GSS02, which gives some results from the General Social Survey back in the year 2002. Recall that the General Social Survey is a biennial study that's done in even-numbered years. It's a large study consisting of face-to-face interviews with thousands of people. Not all of them are asked the same set of questions, but generally for any given question in the study, quite a few, hundreds, even thousands, are asked that particular question. In 2002, a lot of people were asked whether or not they approve of the death penalty, and the results were recorded in the variable kapun. That's a factor variable with two values, favor and oppose. If you run xtabs on kapun with this data frame, you find that of the people who responded to that question, 899 said that they favor the death penalty. 409 said they oppose. That total is 1,308. Now, 899 out of 1,308 is 68.7%. So that would have been our estimate for the year 2002 of the proportion of people in the population who approved the death penalty. The General Social Survey usually asks about capital punishment, and in 2012 a lot of people were asked. This time, 1,183 said that they were in favor, and 641 said that they opposed the death penalty. That's a total of 1,824. Now, 1,183 out of 1,824 is 64.8%. That's a smaller percentage than back in 2002. So we have this research question. In the United States population, did support for capital punishment decline between 2002 and 2012? It's very important to notice that this is actually a question about the relationship between two factor variables. We're not just thinking about kapun in this research question. The explanatory variable is actually the year under study. It's a factor variable with two values, year 2002 and year 2012. The response variable is one's opinion about capital punishment. That's the kapun variable in those data frames. That again is a factor variable with two values, favor and oppose. Since both variables have two values, we can be interested in a difference of population proportions, P1 minus P2, if we set things up right. So in our significance test, we start off by defining parameters and stating hypotheses. Let's let P1 be the proportion of all U.S. adults in 2002 who support capital punishment. And let P2 be the proportion of all U.S. adults in 2012 who support capital punishment. If you think that the proportions out in the population have not changed over the years, then you think that P1 equals P2. And so you would think that P1 minus P2 is 0. Let's let that be the null hypothesis. We'll do a two-sided test, so the alternative will just say that P1 minus P2 is not 0. As for the code, it's the same as what you would do if you had summary data and were interested in a confidence interval for P1 minus P2. You just need to put the summary data in correctly. So we call up prop_test_gc, the same function that gives us confidence intervals for the difference of two population proportions, and we use the x in the n argument the same way as we did for confidence intervals. So we make a list of our successes and a list of our sample sizes. The only thing you have to be careful to do is make sure the elements of the list match up. Year 2002 came first when we specified X. It also needs to come first when we specify the sample sizes. If you want that test of significance, you add that third argument specifying the null hypothesis's belief about the value of P1 minus P2. So we set the argument P to 0. When you run this code and look at the output, we'll go right down to the inferential results here. We see that P1 hat minus P2 hat, our estimate of P1 minus P2, worked out to about 0.038. That's about 3.8%. The standard error for P1 hat minus P2 hat is about 0.017, about 1.7%. Let's think about this. The null hypothesis is expecting that P1 hat minus P2 hat should turn out to be about 0 because that's what it thinks that P1 minus P2 is. We actually got P1 hat minus P2 hat being about 3.8%. The standard error was 1.7%. So our results are a little bit more than 2 standard errors above what the null hypothesis expected. So these are somewhat surprising results, if the null is right. Looking at the confidence interval for P1 minus P2, it extends from 0.005 to 0.07. That's from about 0.5% to about 7%. Notice that 0, the null's belief about P1 minus P2, is below this interval. This is advance notice that we're probably going to be rejecting the null hypothesis. The test statistic again is called Z, and I'd like to talk a little bit about how it's made. The actual formula for it is P1 minus P2 hat, those should be hats there, divided by the standard error for P1 hat minus P2 hat. As we'll see in a minute, this constitutes an observed difference divided by the standard error for this difference. So it's Z-score style yet again, and it's going to tell you how many standard errors P1 hat minus P2 hat is above or below what the null hypothesis expected. Let's think a little bit more about how that test statistic works so that we can see how it connects to giving us a p-value. We already know from our work back in Chapter 8 that as a random variable, P1 hat minus P2 hat is approximately normal as long as your sample sizes were pretty large. Also, we know that the expected value of P1 hat minus P2 hat is P1 minus P2. Now the null thinks that that difference is 0. So if the null is right, the expected value of P1 hat minus P2 hat is 0. Now let's take a look at Z. Its formula is this, and again, these should be hats on the top. Very sorry about that. The P1 hat minus the P2 hat could be written as P1 hat minus P2 hat minus 0. Subtracting 0 changes nothing in the arithmetic. But now we've got it expressed as what you got in your study minus what the null expects you to get. Now, the denominator of Z is the standard error for P1 hat minus P2 hat. At large sample sizes, the standard error should be a pretty good approximation for what it tries to estimate, namely the standard deviation of P1 hat minus P2 hat. Therefore, the fraction that makes up Z should be approximately this fraction here. In this fraction, what you're doing is taking P1 hat minus P2 hat, subtracting off its expected value if the null is right, and dividing by the standard error. So you've standardized it. Since P1 hat minus P2 hat was approximately normal, when you standardize it, you're going to get approximately the standard normal random variable, the one with mean 0 and standard deviation 1. So that's why we're going to use a standard normal random variable to come up with approximations for the p-value in this test. The p-value turns out to be 0.0228. Again, we need to interpret it carefully. If support for the death penalty remained constant from 2002 to 2012, that's our way of saying if the null is right, then there's only about a 2.28% chance of getting a test statistic at least as far from zero as the one we actually got. Since the p-value is smaller than 0.05, we're going to go ahead and reject the null hypothesis. So the general social survey data from these 2 years provided strong evidence that support for the death penalty declined a bit between 2002 and 2012. Let's try another example and see what it teaches us. Say we have this research question. At Georgetown College, who is more likely to believe in love at first sight, a female or a male? In the Math 111 survey data, we have the variable sex, male-female, but we also have the variable love first, in which people answered the question, do you believe in love at first sight, yes or no? 2-factor variables, both with 2 values. If we make a cross table for the relationship between sex and love at first sight, we get the results as follows. If we look at row percents for this cross table, then we see that of the females, 45% believed in love at first sight, nearly half of them, whereas of the males, only 25% or so believed in love at first sight. 45% versus 25.81%. That's about more than a 19% difference. That seems like a pretty big difference. Let's do some inferential work here. Is that difference so big that it can't be explained just as chance variation in the sampling process? Let's let P1 be the proportion of all Georgetown College females who believe in love at first sight, and let P2 be the proportion of all Georgetown College males who believe in love at first sight. If you think that what sex you are makes no difference in your likelihood of believing in love at first sight, then you would think that P1 equals P2. So you would think that P1 minus P2 is 0. Let's let that be the null hypothesis. And we'll do a 2-sided test here. The code comes from prop test GC, just as it would for confidence intervals. This time we have a data frame to work with, so we use formula data input in just the same old way as we do when we investigate the relationship between 2-factor variables. So twiddles, explanatory, plus response, and then data is the name of the data frame where those variables are housed. We have to be careful to specify what we're counting up here. Since we're looking at the proportions of males and females who believe in love at first sight, we're counting up yeses. We need to tell the function that yes shall count as a success. We want to do a test, so we need to add in the p argument, and the null hypothesis thinks that P1 minus P2 is 0. If you were to run the code, you get descriptive results first. Two-way table is repeated, but also the p hats, the estimated proportions, are given as well, and so we see that 19% difference. But notice also, when you're thinking about safety checks, you need at least 10 successes and at least 10 failures in each of your 2 samples before you can really trust the confidence intervals and the approximations for p-values that these tests deliver. Well, we have 8 males who believe in love at first sight. So in the male sample, we have 8 successes. That's less than 10. If you actually run the code for prop test GC, and you probably should just to see what will happen, you'll see that the machine computes all of the confidence intervals and p-values for you, but it also delivers a warning and suggests the use of some simulation. So what should you do? Well, we happen to be dealing with 2-factor variables here. Sex and love first are both factor variables, and fundamentally we're studying the relationship between these 2-factor variables. We have the old chi-square test way back from earlier chapters for testing whether a relationship that we see in data between two-factor variables might hold out in the population from which those data were selected. So we could run chi-square test GC here using the same formula data input. But since the sample sizes apparently were somewhat small, let's do simulation. We're looking at a random sample here from a population, so the way we do the simulation is the type random. Specify a good number of chi-square resamples, several thousand, and if you'd like, you can get a graph of your resamples and see visually how often they exceeded the chi-square statistic that comes in your actual study. So this will give us a perfectly good test of significance to see if sex makes a difference in belief and love at first sight. But chi-square tests don't deal directly with parameters, and so there's not going to be a confidence interval for P1 minus P2. Just another note or two. Since prop test GC can deal with the difference between two proportions, there's the question about which population comes first. When you define your parameters, you define a certain population to be first. If you want the function to honor your conception of what the first population is, then you need to use the argument first in the function. So for example, if you wanted the males to be the first population in this test of significance, say you wanted P1 to represent the proportion of all Georgetown College males who believe in love at first sight, then you would need to set the argument first to male. Also, if you would like less output to the console, if you just want enough information to get the confidence interval, test statistic, and p-value, then you can run prop test GC, but with an additional argument verbose set to false. Thank you for listening.